Okay, hopefully it started recording. So, hi everyone. Thanks for joining this colloquium, the first colloquium of the year. And today we have invited Dr. Ewan Cameron, who's an associate professor at Curtin University. And just to briefly introduce him, he did his PhD at ANU on galaxy formation and evolution from high to low redshift. And after a couple of postdocs at St. Andrews, ETH Zurich, and he moved on to work on Bayesian methods at QUT in Brisbane. And then he moved on as a senior computational statistician for the Malaria Atlas project at Oxford and now in Perth. So he's been like switching fields between statistical methods in astronomy and various fields over his career. But today he will be talking about mostly, I think, on his astronomical side of things. So yes, thank you, Ewan, and please take it away.
Great. All right. Thanks for I'll just check for the last time that you can all hear me okay?
Yes. Brilliant.
Okay. And yeah, if it displays under the name Emily, that's my wife, not me. It's not a alter ego or or a pseudonym. It's just a borrowed computer at the last minute. So yeah, the talk I'm going to give today is a bit more of a review talk rather than a talk describing specifically a completed piece of new work. What I was hoping to do was to focus on the topic of model misspecification in a way that would be like relevant and interesting to an astronomical audience by coming at it through the lens of photometric decomposition models. And then in introducing it this way, I'd like to look at some, like a mini survey of some approaches from the recent applied statistics literature for dealing with model misspecification, and probably concluding with with something of a loose argument that I have that we need to think about using some more general Bayesian style updating procedures, for the types of models that we're fitting, maybe more so than a very strict, say, conventional Bayesian style of modeling. The question is, how do I, oh, there we go. Okay, so this is the outline of the talk. Like this slide, there'll be a lot of very wordy slides, which I'll probably skip through, but I'll make sure that the PDF's available, for people to take references, which I put throughout. So I'm going to begin with an introduction to photometric decomposition and model misspecification. Then I'll move on to some specific examples from the photometric decomposition literature of ways that it seems the models might be misspecified, and a particular example which I worked on from a Nature Astronomy sort of paper, and then a Matters Arising, looking at a case where I think this issue has caused problems in the past. And then finally, I'll go on to look at those sort of methods from the applied statistics literature for dealing with misspecification and model building. So, and then finally, the comments of where I think this leaves us for photometric decomposition studies. So to start with, for those of you who aren't big fans of photometric decomposition, the justification for photometric decomposition studies would be this. The stellar material of galaxies is observed to be arranged in a variety of ways. So when depending on the band we observe in, we see some very striking morphological features, these substructures like bulges or disks or bars and spiral arms. Importantly though, these morphological substructures are distinct from one another in ways which have a somewhat of more of a fundamental physical interpretation in terms of things like the ages of their stellar populations or the kinematics of their constituent stars. So we think that essentially the different morphological features and structures we see reflect different formation pathways. And so that's this sort of simple justification for this field of research. So just a couple of little examples I clipped from the literature here. one would be the case of a buckling bar forming a pseudo bulge out of an otherwise relatively featureless disk, or the pathway to formation of ellipticals, and notionally also classical bulges by the merging of two, say, like disk galaxy progenitors. So photometric decomposition studies aim to use mostly parametric models for the intensity distributions of these morphological subcomponents in a way to isolate them and characterize them quantitatively within a galaxy image. So this example here would be a one-dimensional decomposition of the galaxy NGC 4736, in this case into 4 components, into a bulge, a bar, a disk, and a ring. And you can see, for example, so on the y-axis is surface brightness, and on the x is sort of galactic radius from the center of the galaxy. So the exponential disk in this case, with sort of logarithmic surface brightness units, is the straight line, which dominates particularly at the outer radii. Then there's a centrally very concentrated bulge, so with a very steep light curve, and then the ring and the bar are sort of modeled as some somewhat more concave components that that fit in there at intermediate and large radii. And so you'd fit a model like this, and the estimated parameters of things like the disk scale length is what you'd take away to do science with. So looking at very nearby galaxies with excellent resolution images, mostly HST imaging studies, there's photometric decomposition has provided us with a range of very interesting results. Things like the one shown here, which is the correlation between the stellar luminosity or the mass of a classical bulge and the mass of the central black hole. Likewise, we have results on, for example, these so-called pseudo bulges, which are bulges visually classified in this case as having some type of inner structure rather than being completely smooth. These ones have been found to be flatter through photometric decomposition modeling studies than their classical bulges, so having a different sort of shape of light profile. And this is argued as evidence for them having different formation mechanisms. So I've called these ones the supervised photometric decomposition studies, because these ones are really ones where they're the components of the model and the sort of the starting conditions and the details of the fit are very heavily supervised by hand before sort of as, I guess, starting conditions for then what is eventually an automated fitting procedure. When we turn to large-scale galaxy surveys, the nature of photometric decomposition is, in a sense, much more automated. And so in these ones, we find results like that the global color bimodality of galaxies seems to be largely a reflection of their two-component nature. In other words, bulges have been shown to be predominantly red and disks predominantly blue. A quick aside here, actually, Paul Allen, who was the first author of this paper, actually is now the sort of a deputy at the health department in the United Kingdom. And the past year or so, or more, in fact, he's been working flat out on their COVID response, coordinating the translation of modeling results from the epidemiologists to the policymakers. So that's pretty cool work by an ex-astronomer. Anyway, this is a brief aside. The automated studies of photometric decomposition have shown things like this, that the disks of barred galaxies are significantly bluer than those, the disks of unbarred galaxies are significantly bluer than those of barred galaxies, even though their bulges seem to have a very similar color distribution. And then we get results like this, like looking at the luminosity size relationship of galaxy disks as a function of how dominant their bulge is. And then finally, we use these large-scale photometric decomposition studies to make sort of like census studies of where stellar mass resides in the local universe. And it's been shown in the gamma survey that it seems to be roughly half of stellar mass locally exists in spheroids and the other half in disks. So all of these results then can be used in a number of ways to constrain models of galaxy formation, which would be the core scientific outcome of this type of study. So then changing tack a little bit, I'd like to talk about what do we mean by model misspecification and what are its consequences. So these likelihood-based statistical methods, whether we're talking about Bayesian inference or maximum likelihood, very popular within astronomical science and lots of other applied statistical kind of studies in literature. And they offer very powerful techniques for fitting models and for quantifying their uncertainties in a rigorous way. So to proceed with these methods, the sort of the foundational assumption that you have to have is that you need to choose a parametric family of distributions, of sort of probability distributions, from which it's supposed that the observed data were generated if only you could discover the right choice of parameters. So a typical example might be for a linear regression that we imagine the observed data, the y's, each one is normally distributed about a mean, which is has some covariate x multiplied by a slope, and it has a fixed, perhaps known standard deviation. And then we, in a Bayesian context, we'll put a prior on the slope parameter, and we'll use the machinery, the likelihood-based machinery of Bayesian statistics to come up with an estimate of what likely values of that beta slope parameter were. So the case of misspecification occurs when this assumption has been made incorrectly. So we've assumed a certain range of data generating distributions in a parametric family, but in fact the way the data were generated doesn't correspond to any choice of the parameters in our model. So to go back to the linear regression example, we might have misspecification in terms of we've chosen the wrong likelihood function. So in fact, maybe the sort of the noise is much fatter tailed than a normal distribution. So it actually comes from something like a student's t distribution. So we've made a mistake there, and there'll be some extra noise in the data, which our normal model isn't accounting for. Or alternatively, we might have the case that in fact we misspecified the regression relationship, the true relationship by which the data was generated, and it's something more of it has like a quadratic additional term like this. So in the former case, when the model is well specified, then whether we're doing Bayesian inference or sort of more frequentist, maximum likelihood style interest in this case, there's a lot of theoretical results that confirm to us that we're on relatively safe ground in the way that these things are used. So in particular, for sufficiently well-behaved models, we have that the maximum likelihood estimator converges towards the true parameter value as more and more data is added. And it's even better than that in the sense that we also know that the maximum likelihood estimator is asymptotically distributed with a normal shape, sort of a normal distribution. And the variance of that is proportional to the inverse of the Fisher information matrix. So this is certainly well used in studies of weak lensing and so on, as far as designing new experiments. And it's a foundational result of a lot of frequentist testing procedures and so on. There's lots of other results for different special cases. Cases like when the true parameter lies on a boundary in a restricted parameter space, or and even for special cases where we have we're looking at the partial likelihood scenario where it's a maximum likelihood estimator that some other part we're going to marginalize over is infinite dimensional. So this would be like a highly non-parametric model, like this so-called Cox proportional hazards model in survival analysis. Maybe, I don't know that I've seen it used in astronomy, but certainly it comes up a lot in the epidemiology setting. So that's for this is all for the maximum likelihood case. In the Bayesian case, we are also lucky because there's theoretical results to show that for the most part, the data will eventually overwhelm a poorly chosen prior, such that the Bayesian posterior concentrates towards the asymptotic distribution of the maximum likelihood estimator. So this is also very reassuring for Bayesian analysis, and in some ways is often used as a justification for Bayesian methods, in the sense that the prior helps us encode sort of our prior knowledge and ensure that with small amounts of data the model is well behaved and regularized, but that if we've messed up the prior, as we add more and more data, our kind of mistake will be shown to us, and the data will speak for itself. So just, I guess, a note on like terminology for people who haven't seen these type of results discussed so much. If you want to look at them more in the literature, results on the convergence of the posterior towards something asymptotically normal are usually called Bernstein-von Mises theorems, and regularity conditions, which mathematicians add to make sure that the likelihood will eventually dominate over the prior, are often called Schwartz conditions. And then finally, we can say also there are a lot of literature studies on what happens to non-parametric Bayesian models in the asymptotic limits, and they often have quite reasonable frequentist properties, but there are certainly pathological examples where that's not the case. But yeah, so in the well-specified setting, we're pretty happy. But the question then is, what happens to our parameter inferences when we go ahead and we fit, presumably unknowingly, but not always, a misspecified model? In brief, the sort of take-home summary is that these previous results don't apply, and we risk the case that the parameter estimates might be biased, and that the uncertainty intervals we get might, in some sense, have the wrong width. So there's also a lot of theoretical results to try to make those statements more concrete. And perhaps the most important one is that whether we're talking about the maximum likelihood estimator or the Bayesian posterior itself, for a class of sufficiently well-behaved simple models, we know for sure that that asymptotically, as more and more data is added, the maximum likelihood and the Bayesian posterior will converge towards a set of parameters, and we can sort of say something about what this set of parameters looks like, which is that it's the set of parameters under the proposed model for which the implied generating distribution, so for which the model for the observed data minimizes the Kullback-Leibler divergence against the true generating distribution. So the way that this would be could just be written down in notation is in the middle of the page here. Basically, if we suppose that these data, the y, subscript I, are drawn IID from some probability distribution P, so that's our model. That's a mistake. If in fact the y are drawn from this P, which we don't know, but that's how they were generated, and we mistakenly assume that they were drawn from some family of distributions Q, which has the parameter theta, then asymptotically, whether we're talking about the maximum likelihood estimate or I actually said map there, that's not quite correct, but a Bayesian estimator, say the posterior mean, for example, we know it will converge to this point theta asterisk, which is defined as the theta minimizing this term here, which is the Kullback-Leibler divergence. So this integral of the log ratio of probability densities between the true model, unknown, and the proposed model family. And it's an integral with respect to the true model. So it seems like a bit of I'm not sure, a bit of an abstract, kind of artificial thing, and it's like why would it be this? So the reason that I guess it can actually sort of one way to understand it is to see that the Kullback-Leibler divergence is simply it's a name for this thing. It's a name for a distance between distributions. And why does it happen to be this one? On the bottom of the page, we can sort of take the back of the envelope type of argument that Stephen Walker gives, which is that we're maximizing the likelihood, and what we're maximizing it against in the in practice is against the distribution of observed data, so the data we have. So you can consider this distribution of observed data we've been given as an approximation to the true distribution from which that data came, and it's sort of, we call it the empirical distribution. So simply this term of maximizing the log density in the parametric model we give is equivalent to minimizing its inverse. And then if we add on the py term in log space, it's not changing anything. So it's a result which, in a sense, well, the convergence results are important because they show that it converges. But this notion of the Kullback-Leibler divergence minimizing point, it's useful because it lets us say, what might this point look like given what we know about Kullback-Leibler divergences? And so I'll come back a little bit to that later on. So the big problem with this misspecification arises when this theta star, where the posterior or the MLE are going to converge to, doesn't coincide with why did I write that? That's silly. The problem is that this theta star isn't necessarily what we're understanding as to be meant by the parameter theta. So actually, I'll revise that sentence about the inference being inconsistent. That's a bit poorly said. Essentially, it's that we don't know what this theta star actually looks like in the sense of our model family. That's probably a better way to say it. So the model's going to converge somewhere, but it may not be where we sort of envisage it to be converging. So then the real question then is, what happens to the posterior variance? So again, with a lot of assumptions about to make a relatively simplified case that can be studied through theoretical means. In the misspecified setting, the maximum likelihood estimator converges in distribution to a normal. So we get another one of these Bernstein von Mises, one of these Volt type convergence theorems. So it's we know that it'll be well behaved in a sense, at least it'll be normal. And it converges on something which is centered, as I said before, on this KL minimizing set of parameters. And it will have a variance proportional to this term here with these J's and I's. And the way that those are defined, the I's is the covariance of the gradients of the log likelihood. And the J's are defined as the negative expectation of the second derivative of log likelihoods. So if you've seen Fisher information, the sort of formula for Fisher information before, like used in weak lensing, then these should be quite familiar. If not, they may seem somewhat arbitrary. But in the well-specified setting, the I and the J are just two interchangeable expressions for the Fisher information. Actually, it would be kind of weird to even write them differently, that it would just be the same thing. And so the model would have the right sort of posterior variance. In the Bayesian setting, we have this problem that we know that although the posterior will converge on something centered about the KL minimizing set of parameters, its posterior variance will be proportional to just the just this J term, not the full J times I times J part. And so unless there would be some lucky reason that that these agree, we find that the Bayesian posterior will very likely be the wrong size, meaning that the statements we go on to make about credible intervals can be such that they're either way too confident or they're underconfident relative to how they should be. Then just finally, the last point on this sort of somewhat theoretical discussion is what happens with model choice under misspecification. Broadly speaking, it's exactly the same as for parameter inference, which is that the posterior odds ratio of the two misspecified models will diverge to favor the model with the lowest KL divergence against the true data generating distribution. So it will choose a model, and this model will be defined by this property. The main take-home message I would put on this slide is the one in bold, which is to simply say that given two bad models, the data will eventually strongly favor the least bad model in this KL divergent sense. And that is not really satisfactory. Like we need to know, how bad the models are, and simply showing that one model, like a bad model, has been preferred over a worse model isn't sort of a sufficient justification that we should use this preferred model for science going forward. So this dissatisfaction in, I guess, the convergence or the nature of Bayesian model weighting has led people to start looking quite recently at into alternative non-Bayesian or semi-Bayesian kind of methods for dealing with these terms, like for model averaging. So we have examples such as using this technique of stacking proposed recently. So to come back to photometric decomposition studies, we have to say photometric decomposition models are almost certainly misspecified in a number of ways, and in a sense quite obviously so, because to make fitting practical and effective in the sense of coming up with terms that we can comfortably fit with our computational budget, and which we can make sense of as archetypes, we tend to make a lot of simplifying assumptions about their morphologies. We basically always assume that bulges, disks, and bars are very smooth, so they have no spiral arms. We often neglect things like lenses or nuclear star clusters and other things. We suppose that bulges follow a Sersic profile, and sometimes we even fix the index of that profile. And we suppose also that the disks have an exponential form which continues all the way to the center of the galaxy, and generally speaking, all the way out towards infinity. So we don't usually work with inner or outer truncations. And when we fit this kind of model, like the one shown here, the model comes, so we have the observed image on the left, the model in the middle, and then we get this residual on the right. And there's often a huge amount of structure there, so that we can see the model is not an adequate representation of the complexity of the galaxy image. So this is sort of a misspecification of the regression component of the model. There's also quite a few ways in which the likelihood could be considered a misspecification, or rather like a pseudo likelihood, even though we're going to treat it, or even though we often treat it as a normal likelihood. So for example, we have these observed pixel values, which might be assumed to have some sort of Poissonian distribution, but this will often neglect the impacts of drizzling, or maybe we don't even really have a good idea of what the ratio from counts to sort of pixel values really is in the image, and it doesn't include the effects of things like methods for say removing neighboring galaxies, or the contribution of neighboring galaxies to the light profile, and this sort of thing. Generally, we'll use a normal approximation to the Poisson. So not strictly working with the Poisson. And it can be even more complicated because often the sort of the variance that we assume for the during fitting comes from simply the observed photon count rather than that which is model predicted. So it's also likely on a pixel by pixel basis to be sort of somewhat misspecified as well. But we do conduct fitting within strictly within a likelihood or pseudo likelihood based kind of framework. Often that's Bayesian, which generally means the priors are used to kind of restrict the parameter space towards sort of physically meaningful fits. So for example, to make sure that the bulge doesn't grow in scale length beyond the disk and somehow that the two get swapped over and that the exponential piece doesn't start modeling the center of the galaxy and the Sersic profile, the outskirts, that sort of thing. So I'd like to talk briefly about a case where I think this has caused problems in the past. So there was this study in Nature Astronomy, which I wrote a Matters Arising on, which is kind of the basis for the following. So this study looked at the fits of radial acceleration relationships to some radial velocity data from galaxies in this spark sample. And what they looked at was they fit MOND-inspired radial acceleration relations to the radial velocity data. The models that they fit were based on bulge disk decompositions or profile fits that had already been created. And so then the free parameters of this downstream analysis were in terms of like the mass to light ratio of the bulge and of the disk, as well as this universal acceleration parameter under the MOND style model. Yeah, so this is the way the bulge and disk luminosities were estimated. Basically, they were computed from near infrared imaging by a two-step process where an exponential disk was fit to the outer part of the observed light profile, and then the bulge was defined non-parametrically as any central excess rising above that disk. So then, allowing for some uncertainties on the disk inclination and the exact distance to the galaxy, the Nature Astronomy authors came up with a 5-parameter model with a sort of chi-squared looking log likelihood function. And they fit that to each galaxy in the sample, and they looked at these, the marginal posteriors for this universal acceleration parameter for each of them. And this was the, I guess the key plot from their paper, which is that they lined up in order of increasing or increasing median posterior value for the A0 parameter, all the posterior credible intervals for each galaxy that they had for A0. And they plotted, and on top of that, they plotted their sort of pooled estimate, which was from combining all of these fits together. And they found that the credible intervals at a given sort of level typically didn't overlap the pooled estimate at a frequency of times that corresponded to that level. So for example, when they looked at the 3 sigma credible interval, they would expect that it was covering over 99%. It was covering the pooled estimate 99% of the time, and they found that in fact it only covered it about 69% of the time. And they concluded that for this reason, the MOND-inspired radial acceleration relationship couldn't possibly be correct. So the main problem with this, in my estimation, is that they're fitting a misspecified model. So if we look at the, they only give one example of what the fits look like in the paper, and it's this one here. You can see the radial velocity data in red, and then the black line is the model fit. And this is the best fit of the model to that data, and it's clearly nothing like the actual observed data. So, which could come from a variety of limitations. Most likely, or at least one part, must be the limitation of the photometric decomposition. And so you have this model which is completely misspecified, so we can't make assumptions about the performance of the credible intervals as if they should have the correct width. And so that was the argument that we put in our matters arising. All right, so now I'd like to just briefly say a couple of things about how we might diagnose misspecification. I've said before in the case of photometric decomposition that you can simply look at the residuals, and this presence of structure, of sort of non-random structure, is a very clear sign. But that's actually also, using visual diagnostics is essentially also, I guess, the most powerful way to search for misspecification and so on in a more in a sort of Bayesian model, which is not so directly fitting something in a visual context like a galaxy image. So there's a good paper by Gabri et al. 2019 where they look at these posterior predictive check diagnostics you can do. For instance, comparing the distribution of data simulated under the fitted model against the distribution of observed data. In this case, they find that the simulated data in gray from their assumed normal fit it's way more symmetrical than the observed data. And so you might say, well, if we're interested in quantifying the sort of location and the peak of this distribution, we might want to start looking at a model that has some degree of skewness. So this couple of slides are just to emphasize that ultimately, although there are posterior predictive checks that put numbers on sort of like the discrepancy, that ultimately it's a visual diagnostic that really, I think, makes the most impression, helps the model building. So what do we do when we identify model misspecification? The most common process, or the most common thing that you would do in a Bayesian analysis is that you would revise the model in some way. So this isn't an automatic procedure. It's sort of the human element of applied statistics, and where kind of experience and having seen a lot of other models starts to pay off. In the Gabri example, they start to look at, say, okay, if we have this mismatch where sort of asymmetry is the problem, let's look towards maybe fitting like a skew normal distribution and working in that direction. If we would translate that to photometric decomposition studies, the natural extension would be to say, well, we should add more components, some lenses, rings, and bars. But unfortunately, there's a lot of limits to what we can do with this in terms of particularly the stability of the fit starts to break down and the computational cost starts to increase a lot. And even with many components added, we have lots of examples from the literature where the residuals are still very large and structured. So although it's made some improvement, it's very hard to say that this is, we certainly couldn't say that this is the end step for this type of process. The other thing we could do is to consider adding a non-parametric spatially correlated error term, for example. So to say that all the things that aren't modeled with our smooth galaxy image come from some non-parametric distribution, which might be like a Gaussian random field. And this is the approach that we use quite a bit in the disease mapping. I couldn't in the time I had find an astronomical example of this, but I suspect that it is. I suspect that there are a lot of examples in astronomy that I haven't seen, which follow this process of adding some type of non-parametric noise term. The motivation, I guess, the aim of going to a non-parametric model is that you're trying to broaden your model class so much that the true distribution is by definition contained within it. But unfortunately, that doesn't solve all our problems because the posterior asymptotics of these non-parametric models has its own challenges, and often the true distribution may still not be within the very large class that we've assumed. So then, in the recent literature, there's been kind of a return to enthusiasm for bootstrapping type of measures, which used to be very popular in astronomy. So one method to try to deal with misspecification is this technique called Bayesian bagging, in which we don't just look at one posterior, we look at a pooled set of posteriors formed by making bootstrap replicates of the observed data set. So this is focused on the IID setting, so where all the observations are sort of identical, so we're not really focused on the regression setting here. So the idea is this, like bootstrapping means sampling with replacement. So we're going to make these mock data sets, which are resampled versions of the original data set. If we just do this and resample, so if we have n observations and we resample with replacement for another n, obviously we'll have copies and there'll be some missing. And we combine these posteriors, then the posterior variance will almost certainly be too large if we were using the correct model. The reason is because we'll have for each posterior its posterior uncertainty width, plus then they'll all be shifted around with extra noise due to the resampling process. So interestingly, it turns out you should if you're doing the Bayesian bagging method, you actually want to resample, make mock data sets that have more than the original number of observations. And so in this paper, Huggins and Miller give a useful formula which lets you choose a sensible resampling size, somewhere between the size of the original data set and double it in the worst case scenario. There's a lot of related methods to this as well. They don't have to strictly be actual resampling. They could be things like this weighted likelihood bootstrap, which I won't explicitly talk about, but I give some references there. And in all of these cases, the idea is that a little bit like sort of the back of the envelope derivation of this convergence to the KL minimizing point, is that we can use the empirical distribution of the observed data itself as some type of approximation to the true data generating process, and use this to try to robustify our inference. In all these examples, the method is targeting better coverage of this KL minimizing parameter. So trying to solve the problem that the width of the credible intervals might be too large or too small to cover this one. But we also have to step back and see whether that whether having a fit, in this case, say a fit which is ignoring a bar or ignoring outer rings, actually is doing the job that we want for our inference purposes. I'll talk about that a little bit later on. Another way that people have been trying to deal with misspecification is with this idea of posterior coarsening. So the idea actually comes independently, but looks in a way quite similar to approximate Bayesian computation, which is also starting to be well used in astronomy. And the idea is that instead of doing the Bayesian updating conditioning on sort of the exact observed data set that we have, is to condition on a neighborhood of the observed data. So imagine that, in a sense, that not just that this is the data we observed, but we kind of could have observed any data which was sufficiently similar to that, in a sense. And so then they show, Miller and Dunson, that if the sense in which you define the similarity is in terms of relative entropy, then it argues for a method where you actually power down the likelihood in your Bayesian inference. So instead of having the posterior be the likelihood times the prior, it's the likelihood to the power of beta, where this beta is something that you actually decrease as you get more data. And in fact, under this setting, the posterior doesn't, as you add more and more data, the posterior doesn't actually concentrate to a single point effectively. It stays with a finite width, which is in their sense intended to reflect the idea that there's this contained and unresolved uncertainty about the true model. There's also a variety of techniques which then kind of build on this, such as this so-called Wasserstein ABC method, where instead of targeting the relative entropy as the closeness of allowed data sets, they target this Wasserstein distance or Earth movers distance, which may have some advantages, such as being less sensitive to distributional extremes than the KL divergence. And actually, I will try to say at the end, I think that there's a lot of, potentially a lot of value in this, in the photometric decomposition case. So I'll say why in a minute. So yeah, those are some things that people have been doing in the literature. But again, these are all for the case of this IID data, which is not what we have here. We have data which has lots of different variances, and potentially, the skewness might depend also on other aspects of the data. So the data in photometric decompositions isn't in this setting. So we can't just simply take these techniques like the bagging or the coursing, which I've mentioned, and translate them one-to-one onto our problem. But I think they do give us a family of ideas to work with. What I think we need to do to perhaps improve or increase the value that we're getting from photometric decomposition studies is to focus on what are the objectives of our downstream inference. So we're going to learn these parameter values for bulges and disks, but we first need to think about what are we actually going to use them for. So for example, are we going to learn stellar mass functions by components or construct mass size relationships, or are we going to make a comparison to theoretical models? Maybe in a direct sense, like fitting one model on the observed data and another on sort of mock images from the theoretical model might be the way the analysis goes. And with that context, we can then look at questions like, do the parameters of our models as we're fitting them in the misspecified setting actually have the interpretation we desire for them? So in one sense, that would be looking at when we fit bulges to galaxies, and the bulge, and we don't include a bar. All these bulges are when there's barred galaxy, the bulge is going to be picking up barred light. So it's mixing something which is notionally sort of rotationally supported against something which is velocity dispersion based, and so we're muddling the waters there. So in that sort of fairly obvious setting, we wouldn't have the interpretation we desire. But it might be less obvious when we start to look at exponential, at disks, for example. We might not really mind that we ignore the outer truncation, or potentially we might not mind that we're ignoring inner truncations and classifying bulges in some sort of by definition or by photometric definition way, rather than as a by velocity dispersion manner. And so then when we think about how do we look to develop alternatives or modifications to the inference procedure, can we design those so they result in credible intervals which are actually better suited to the purpose that we're going to use them? And so the way I think about this is that it makes sense to look at our photometric decomposition posteriors, or under modification, some kind of modified posterior object, like basically all the summary data that we make about these decompositions and their parameters themselves. We should think about them as data for the downstream inference task. So there may be certain parameters which should be prioritized with regards to improvements. For example, if we're looking at the disk luminosity size relationship, we may really not care about those bulges if the bulge includes the bar or not, as long as that's not causing a big problem with our disk sizes. It might be fine to completely ignore it, and we could even try to focus on making sure that it's the disk sizes, which are size estimates, which are protected against the misspecification. Likewise, if we're thinking about the downstream inference task, we might think that there are particular galaxies that could be prioritized with regards to those improvements. For example, if our interest is in making these per component mass or luminosity functions, and we're going to fit them with a Schechter luminosity profile. We know that the Schechter function faint end is incredibly sensitive to what's going on at the bright end. So we could actually focus on trying to make an improved posterior approximation or uncertainty estimation procedure for those very high mass galaxies. We should also think about when we're kind of giving the photometric decomposition fits as data for the downstream inference, that it doesn't just have to be the regular summary of the Bayesian posterior. We give to the next inference step, we can combine information like, for example, giving some measure of the fit residuals into the downstream modeling step. And so, yeah, the way of thinking about it like this, I think has connections to the frameworks of experimental design and also to these so-called modular posteriors, where you end up fitting a series of Bayesian models, but the later model, like a Bayesian model for the luminosity size relation of disks, isn't fit simultaneously to the actual photometric decompositions. Although if we're being fully Bayesian, there's no reason why it shouldn't be. And we just cut the inference of those two steps. And in doing so, we're no longer following strict Bayesian updating. So to me, it makes sense that we should also consider maybe not being strictly Bayesian about how we interpret the posterior summaries of the first step in the downstream step. And so yeah, that was my last slide. And I guess I went through a lot, and I realized, depending on particularly what type of modeling you're doing, some of it might be quite new. But yeah, and also I just would lastly say it's not meant to be a harangue of bulges decomposition or astronomical model fitting in general. But I think it's more like I'd be curious to open a discussion about some of these methods and some of these issues. But yeah, thank you for listening.
Thank you very much, Ewan. Let's give him a round of applause, or at least virtually. So yeah, we still have some time for discussion. So if anyone has any questions, please raise your hand in the participants thing, or just unmute yourself, or write in the chat box, please.
Hi, Rio. I don't seem to be able to. Oh, I see Eric has typed. Never mind. Eric, go ahead.
It's not urgent. Ilya, do you want to
go? I can wait. You can go first.
So I was interested in your, your discussion with the nature authors on the MOND model, and this is, sort of an interesting episode. And I was curious, just thinking about, how we work together to improve models. In your letter to Nature, did you propose specific alternatives for the photometric fits that could be used instead? And or if not, did the authors or did anyone else follow up on this to try repeating the study with better photometric methods that would lead to more trustworthy conclusions?
Yes, so we did actually, it's not published it was in the supporting information. We just gave, in the submission, we'd certainly dig out and share it. I wrote a very simple script to show the difference between the simple 5-parameter fit to the radial acceleration, radial velocity data, which had been proposed in the paper, and then that plus allowing for an extra residual error term, which was spatially was radially correlated, so a smooth extra variations. And yeah, in that we were able to show that the posteriors were blown up. We didn't go so we just did this for like 4 of the galaxies. We didn't go through every galaxy and then and then repeat it or that sort of thing. So yeah, so I don't think that was sort of kind of well. I don't think we quite got the message across in discussion with not only the original authors, Rodriguez, but actually also some people who I guess agree with it. We're on the same side of us in a sense of saying that this data didn't rule anything in or out yet. James Schomburg and Stacy McGaw were, I guess not that interested. In fact, I know James said that if something needs such complicated statistics to argue it, then it's basically a pointless endeavor. So I'd say not that receptive as yet.
Thanks. By the way, if you're able to send a copy of your slides to Rio to circulate, I'd be curious. There's a lot of nice references and information.
Thanks. Yeah.
And Ilya?
Yeah, thanks a lot, Ewan, for a really interesting talk. Certainly the general stealth bias, as it's referred to in some of the literature, coming from model misspecification and the application of Bayesian inference to incorrectly specified models is an issue that we're all having to contend with. The question, of course, is how do you actually determine whether the model is misspecified, right? So you suggested a few ways of doing that, for example, by doing some form of posterior predictive checking. There, with posterior predictive checking, of course, especially if the model is, let's say, predicts something multidimensional, it's not immediately obvious that you can figure out how to make the plots even visual. Let's say if you're doing it visually, that you can make the plots correctly to catch this. Certainly, I've come across various examples where you make several plots and everything looks beautiful, and then only later you realize, oh, I should have made this other plot, and then it would have been patently obvious to me, a different cross section where I would have seen that things really are misspecified. The other problem is that sometimes even if you make all the plots imaginable, at the moment, right, especially if the model is not necessarily a very physically motivated model, but more of a phenomenological model. Let's say you're fitting the initial mass function of stars and you decide it's a broken power law following Krupa, right? That's a phenomenological model. There's no particularly good theory arguing why it should be a broken power law. It's just very convenient and everybody uses it regularly, but it's still conceivable that despite all of the data we have, it's not quite a broken power law. Maybe it's a broken power law, but broken more times than we know of so far. We just haven't seen good evidence for it. But that could still lead, even if the posterior predictive checks don't show up as the model being clearly misspecified, there can still be a stealth bias when you do inference with this kind of a misspecified model. So is there anything you can do to safeguard against that, against a situation where there is no, from the model itself, it's not obvious that it's misspecified, but the inference could still be statistically significantly biased?
Yep. Well, first of all, I hadn't heard that term stealth bias. That's interesting. I definitely kind of Google to see what type of studies that comes up in. So for the case where particularly we have multidimensional data, and so this would be like the non-IID setting, or in a sense, maybe in the non-IID setting, that would be the problematic one, I imagine. Like, for example, I'm trying to look at misspecification in a model for the cosmological background, where in a sense, you just have one data point. So for this type of thing, I think the posterior predictive diagnostics, they require an expert judgment to create them in something where it's essentially like roughly a Gaussian process type of base model, then looking at these empirical autocorrelation functions. In the spatial statistics that I do, that's what people generally look at, but they have quite poor or quite low power actually to diagnose a poor choice of covariance function. So in this disease data setting, if we have observations from 1,000 sites and we fit some model where we assume an exponential covariance function that is isotropic, then these posterior predictive plots or sort of just classical diagnostic plots actually do quite poorly in telling us that it wasn't really an exponential, it was a Matern function. So there's not a simple solution there. So in a sense, the solution has to be being aware of the misspecification issue and considering looking at the sensitivity of the fits to modeling assumptions, this kind of thing. Yeah, I definitely find like the power law one would be for star formation an interesting case where you may, so it may still happen that you want to use the misspecified model because like it's a, it's kind of like a reference point that works. Like for example, in the misspecification of linear regression models, people often talk about that actually you just want to know the best linear fit for this relationship, and you don't care that the relationship is slightly nonlinear somewhere. So for the power law case, I would say, yeah, that's definitely a scenario where one of these sort of methods to broaden the Bayesian posterior to address the misspecification would be very useful. And it's the kind of context where if you're aware of the misspecification issues or their potential effects, then you shouldn't do something like look at say 5 different star clusters, fit a misspecified IMF model, and then say, well, it's not a universal law because their posteriors don't overlap. Like that would be kind of repeating the flaws of the Nature Astronomy paper. Yeah, I guess that's what I would suggest.
Thank you. Thanks very much.
All right, thank you very much. Are there any other urgent questions? If not, we're already 5 minutes over the hour. So yeah, let's thank Ewan again. And yeah, I think he's willing to answer any questions like by email or anything. If you have any more urgent questions, and yeah, please send me your slides, and I'll circulate that later. I'll also circulate the URL for the recordings of this video, so if anyone's interested. So yep, thank you very much again, and see you next time.
Thank you.
Thank you, Ewan.
Everyone.
Thank you, Ewan.